Okay, so thank you very much. It's an honor to be speaking here. This is, well, a talk about things I've been thinking about that kind of actually connect to Maxim, maybe not in the most obvious way, but while I was visiting IHES 2 years ago, I had many discussions with Ludmil and Maxim on complicated questions in Hodge theory and singularity theory and so on, where I think I've been kind of a complete failure at actually helping advance that project. But on the side, this is kind of basically what came out of some thoughts related to that. So this talk owes, a lot of inspiration debt to Maxim. So what I'm planning to do is tell you first about, what is the general story with various corners of mirror symmetry that this fits in with. What does SYZ mirror symmetry say? And what is the family-Floer approach to homological mirror symmetry? And then I want to focus on something slightly unexpected, at least to me, which is what happens when you relax some of the usual assumptions and you encounter holomorphic disks of negative Maslov index. And then in the third part, I will try to tell you about maybe a Morse-theoretic model for trying to do SYZ and family-Floer theory in this level of generality, but at the expense of losing some other generality that had been achieved before. So maybe this is not the cure-all, but still something.
It will be only update or update and upgrade?
It's an upgrade in some ways, and it's a downgrade in some other ways. It's maybe it should be an update on how I feel about SYZ mirror symmetry rather than an update on the theory. It's an update on my feelings about it, maybe something. All right, so let's start by. So this is the smallest writing of all the slides, but I'm trying to fit in like a lot of buzzwords and concepts on one slide. So first, for people who are new to this, hopefully not too many people here, mirror symmetry is generally the belief that you can translate symplectic geometry on some manifold X, for example, enumerative invariance taken in a loose sense, into algebraic geometry on another space called mirror to X, for example, Hodge theory, periods, things like that. And historically, this began when physicists noticed an interesting duality between Calabi-Yau threefolds, but then this got upgraded to, for example, include the case where your manifold you start with is Fano or log Calabi-Yau, which means, well, it's a variety with a divisor in it whose complement is an open Calabi-Yau, basically, and that divisor represents the first Chern class. And then the mirror is something called a Landau-Ginzburg model, which for us will just mean a space equipped with a regular function on it, called superpotential. So one of Maxim's many remarkable achievements has been to formulate the homological mirror symmetry conjectures, which state that basically one important manifestation of mirror symmetry is that when you have a mirror pair, the Fukaya category of a symplectic manifold you consider should be equivalent to coherent sheaves on the mirror space, or if there's a superpotential, matrix factorizations. The Fukaya category, very briefly, is a way to study intersection theory for Lagrangian submanifolds equipped with extra data in a symplectic manifold. So the objects are Lagrangian submanifolds with additional data, and morphisms are intersections, but then there's a bunch of algebraic structures, beginning with a differential, which count holomorphic disks.
And on the right side, is it derived, like derived effect?
Everything is, well, derived, or it's suitable DG models that upgrade the derived level back to something. Yeah, it was initially stated as a derived equivalence, and then one should actually probably upgrade this to refinements of that. I will not actually have too many categories in this talk, so don't worry. Instead, I want to focus more on the differential geometric counterpart to this, which came out of a work of Strominger-Yau and Zaslow in 1996. A recasting of this is the statement that geometrically mirror symmetry arises from having dual torus fibrations on mirror spaces. The shape of it that's consistent with the story I want to tell is the observation that if you believe in homological mirror symmetry, then you actually have a path to building Cech out of X. Because, well, in algebraic geometry, everybody says everything is about moduli spaces. So to take that literally, Cech is the moduli space of the points of Cech. And the points in Cech live in the world of coherent sheaves by just considering skyscraper sheaves. Now, skyscraper sheaves, as objects of a derived category, if you go through things, the kinds of Lagrangian submanifolds that might match with that conceivably, the best guess is a Lagrangian torus in a symplectic manifold, together with a rank 1 local system on it. And so now these must exist in families in your symplectic manifold, matching with the families of points of a mirror. And so the expected statement is we should have a Lagrangian torus fibration on X over some base B, half-dimensional. And we should be considering objects of a Fukaya category which come from considering the fibers of this fibration equipped with extra data, namely local systems. And so first I will try to tell you about a classical somehow way to produce this, which will yield something I will call the uncorrected mirror. And then we have to account for the fact that the Fukaya category is not just about classical geometry of Lagrangians, but includes holomorphic disks into the story. And so holomorphic disks deform Floer cohomology compared to classical cohomology. And accordingly, the geometry of the mirror should be deformed. One manifestation of that, in the case of Fanos, is that this deformation process builds for you the superpotential that makes it a Landau-Ginzburg model. But it also does other things. And then, to cap it all off, the family Floer program, initiated by Kenji Fukaya a long time ago, pursued by Mohamed Abu Zaid, and then there's other work related by Junwoo Tu and Hang Yuan and other people, tries to recover homological mirror symmetry from the SYZ picture by building, in the situation of SYZ, a functor from the Fukaya category of X to coherent sheaves on the mirror space, roughly by taking a sheaf whose stalks or fibers or something are the family of Floer homologies of a given Lagrangian with all of the moving fibers of the SYZ fibration. This is kind of mirror to understand a sheaf. Well, a sheaf is kind of hard for me, so maybe if you have a vector bundle or something like that, you can look at all of its fibers at points and then understand how this fit into an analytic family. All right. Okay, so I want to place this like around, SYZ mirror symmetry is the central player in my talk. So if I have a Kähler manifold X with an anticanonical divisor D, so something representing the first Chern class, I will assume that it's reduced, no multiplicities, friendly enough, maybe normal crossings. So this is called a log Calabi-Yau pair. And then the first step is to find a Lagrangian torus fibration on the complement of D. And how does this happen? Well, in practice, it happens through various techniques ranging from toric degenerations, tropical geometry. We have a toolkit to try to do these things by now. Then, from this, we will first build an uncorrected mirror of X minus D. And that uncorrected mirror will be literally the space of pairs consisting of a fiber of pi. So, in fact, I could just have said the point of a base B. And then for each point of a base B, I will consider the space of all unitary rank 1 local systems over that fiber, which in the case of a torus, remember the fibers are tori, the space of local systems on a torus, that's essentially given by the holonomies, which are homs from the fundamental group of the torus to U1 for rank 1 case, unitary, and that produces for you a dual torus. So this is going to be an analytic space in a way that I will explain soon, locally modeled on subsets of the algebraic torus or something like analytic torus, I don't know what I should say, k star to the n, where k is a coefficient field that I will tell you about soon. There's some bad news there. And then, once we have this basic template, the next step is to understand how we should modify the geometry of this space Cech. And the claim is these will come from the presence of holomorphic disks in X with boundaries on the fibers.
Well, what is k star to the n?
So k is going to be a Novikov field, some non-Archimedean field that I will use for coefficients in Floer theory, and then non-zero elements to the n. I mean, some maybe gm to the n is your what I should have written or something. Okay. All right. So one thing to know about holomorphic disks in a symplectic manifold with boundary and a Lagrangian is that their behavior, most noticeably, what kind of dimensional families they come in, is governed by a number called the Maslov index. Maslov index is basically a relative first-Chern class, twice a relative first-Chern class of a tangent bundle of the ambient manifold relative to a trivialization at the boundary given by the tangent space to the Lagrangian. And in this setting, because the first-Chern class is represented by this divisor D, the Maslov index for me will always be twice the algebraic intersection number with D. So we can take that as a definition in this talk.
So this is a disk whose boundary maps to the fiber?
That's right, yes. Picture will be there on most of the upcoming slides, but picture is I have a fiber, FB, I have a disk, and it might or might not intersect with D along the way. And so basically, what this tells me is disks that intersect more with D come in higher dimensional families. So the two important cases to have in mind, one is the case where the Maslov index is 0, which means intersection number with D is 0. This is also what happens in a Calabi-Yau, right? Because if you have a Calabi-Yau, C1 is 0, there's just no D. So the effect of these disks will be to deform the analytic structure of the mirror in a way I will explain. And also, they will fix issues with what to do about the singular fibers of the fibration pi. I didn't tell you, but this Lagrangian fibration will typically have singular fibers. How to deal with them is one of the important problems in this field. We will mostly ignore them because this is orthogonal to what I want to focus on.
Sorry?
Yes?
How do you use the Maslov index?
Sorry, so the Maslov index is defined, well, I mean, I'm sure I have time for the definition, but basically, Maslov index, you can take the definition to be twice the intersection number with D. And the claim is that disks of this kind come in a family of real dimension n minus 3, where n is the complex dimension of manifold, plus the Maslov index. So that tells me how likely I am to encounter such disks. Okay? And I have not told you yet how they deform the analytic structure. I will tell you in a bit. Okay? This is 2 or 3 more slides. And Maslov index 2 disks, so the ones that intersect D once, they are the ones that first show up when you take Fanos rather than Calabi-Yaus. They're the most obvious way in which the divisor D enters the story, because, well, when you add D back into your space, you suddenly add these disks. And they are responsible for the superpotential on the mirror. Okay. So the relatively new, at least new to me thing, is that if you have negative Maslov index disks, so things that have a negative intersection number with D, then in fact there are stranger deformations of the mirror geometry that show up in a way that Cech should no longer be treated as an honest analytic space. So just to situate, this is like a little bit of a fringe, conspiracy theory or something. because, of course, D is a divisor. Our disks are holomorphic. We all know that complex curves intersect complex hypersurfaces positively whenever they meet. So the only way this can fail is if actually D is not an honest disk, but rather a stable disk, a union of a disk with some other nodal component, a nodal Riemann surface, which has some sphere components entirely contained in D with negative normal bundle. So you have to imagine there have to be exceptional spheres inside D for this to happen. It doesn't happen in the Calabi-Yau or Fano case, but as soon as you leave those cases, it's a fact of life that these things could happen, and sometimes do happen. Okay, so let's go back to, go through the program. So first I told you this space, X, now I'm calling it X0 check, 0 for like uncorrected, also for just the smooth part, is going to be just defined to be the space of pairs consisting of a point of a base B of my Lagrangian torus fibration, over which actually I'm just going to restrict to smooth fibers. And then I will choose a local system or a flat connection, which I will only care about the holonomy of this thing, which will be a homomorphism from pi1 of a fiber, so z to the n, to u1 over a certain field, which is also the first cohomology of a fiber with coefficients in u1. What is u1 over k? Well, that comes in a moment, as well as the claim that this is an analytic space over this coefficient field k, again, away from the singular fibers. So, okay, what's the field? The field is what's called the Novikov field in a formal variable t. It's all formal power series with real exponents in t, and with coefficients in a smaller field, little k, which is not really that important to us. I like to think of complex numbers, but that's mostly a matter of taste. Maybe characteristic 0 is useful? I don't know. Yeah, probably.
But is U1 the same as GL1 for this purpose?
So wait. So now, okay. So now next thing I need to tell you is this is a non-Archimedean field. So it has a valuation, which is just the lowest power of t that shows up in there, and then U1 means it's unitary for that valuation, which means the leading term is a constant coefficient in little k. Okay. So U1 is the elements of a form. U1 is things of valuation 0 inside k star, which is the things of a form a0 plus some, where this guy here is non-zero. Okay. All right. Why are we stuck with these non-Archimedean fields? Well, there's deep questions about convergence in enumerative geometry. But basically, this is the kind of field over which we can reasonably hope to do Lagrangian-Floer theory. And so then, okay, so how do we do Floer theory over such coefficient fields? Whenever we see a holomorphic disk, or more generally a holomorphic curve, we will assign to it a weight. And so, if you look at the early physics papers or even math papers about this, people used to count holomorphic curves with coefficients exponential of minus their symplectic area, or something like that. And we don't know if this actually converges numerically. So instead, what we do is we put t to the power, the symplectic area. This is the main use of the variable t, to record symplectic area of holomorphic curves. And then we'll also put holonomy weights given by the holonomy. Now we're looking at curves with boundaries on Lagrangians. And so we'll use also as a coefficient not just t to the symplectic area times the holonomy of a local system along the boundary loop of our disk. So why now is this an analytic space over K? Well, basically, first thing to know is that in a Lagrangian torus fibration, the base is actually naturally, the tangent space to the base is naturally isomorphic to the first real cohomology of a fiber. That follows from, you can call that action angle coordinates in an integrable system. You can call that the Weinstein-Lagrangian neighborhood theorem, various things. So concretely what you do is, fix a basis of the first homology, fix a basis of loops in the fiber. And then if you move from one fiber, sorry, the reference fiber was here, to another one, B, follow the trace of that loop that produces a cylinder for you. And that cylinder, well, I can count its symplectic area. Whoops, this is, what did I do? Okay. So the symplectic area of a cylinder should show up in the weights, because if I had a disk attached to the fiber at B0, I can deform it to a disk with boundary and fiber at B, and it gains this much area. And then the holonomy coefficient is the holonomy of my local system around gamma I. I can repeat this for a basis of H1 that gives me a collection of coordinates, Z1, and the claim is these are naturally, this is how I equip my space with an analytic structure. If I change my base point and I change my basis of homology, these things scale by constants and get modified by monomial coordinate changes. Okay. So now, okay, I've said it but not written it yet. The Floer-theoretic weights we will assign when counting holomorphic disks is going to be exactly these variables I will call Z sub beta, which are T to the area times holonomy of the boundary. And these are actually monomials in these coordinates Z1, Zn. The exponents in the monomial correspond exactly to the homology class of the boundary of beta in the chosen basis. Okay. And so now the key observation is that Lagrangian Floer theory wants to have an analytic dependence on these coordinates, basically because you're doing counts of disks, which are kind of, locally constant until they stop being constant. We'll see that in a moment, times these weights, which by definition are monomials in our chosen analytic coordinates. And so this will allow us to, if we do family Floer theory, if we do Floer theory with the varying family of fibers, the quantities that will appear will naturally have an analytic dependence.
What does it mean, analytic function over this field K?
Rigid analytic something, something. I mean, essentially they are locally Laurent series in these variables Zi, which converge when the Zi's are given valuation in a certain domain. Okay?
So is it any basis of the homology or some?
I can pick any basis of the the integer homology. This is fine. If I change my basis of homology, then the coordinates I get will just change by a monomial coordinate change on the algebraic torus. Okay, I'm just picking an, the way I'm doing this is because I don't like to think of an abstract algebraic torus modeled on H1 of a fiber. I'd rather think of it as K star to the n.
So what is the relation to the symplectic, to the area of the...
So the area swept by cycles in the fibers, when I go from one Lagrangian fiber to the next, gives me the valuation of these coordinates. Okay, so if you want, maybe one thing I should say, elements of a Novikov field have a valuation, which is a real number, which is like the smallest exponent that shows up. Same thing on n variables. And if I look at these coordinates, the valuation of Zi is the symplectic area of this like cylinder gamma I obtained by sweeping from that cycle. Okay. If I look at the weight of a holomorphic disk, like further down, valuation of Z beta is the symplectic area of the disk. Okay? So quantities that show up in practice, because we're counting holomorphic disk, will have positive valuation wherever we evaluate them. But the Zi's are coordinates that may have positive or negative valuation because you can move your fiber in any direction you want. And you may have infinitely many holomorphic disks occurring at once, but Gromov compactness basically says every expression you encounter will be a Novikov convergent series because the symplectic areas will have to go to infinity. Okay. All right. So that's kind of all I was planning to say about this space to begin with. Now we need to talk a bit about how holomorphic disks enter into the story. And so the main protagonist for me is going to be this Floer-theoretic obstruction, first studied systematically by Fukaya-Floer, Ota, and Ono, called M0 or mu0. It's the curvature term in the A-infinity algebra structure that Fukaya identified on Lagrangian Floer homology. So what this is for every Lagrangian L, it's an element of a Floer complex of L with itself. Now, what we mean by Floer complex of L with itself, it's some kind of cochains on L with coefficients in K. What kind of cochains? I will leave that unresolved for now. We'll make some choices later. What that is defined, how that is defined, is we want to look at the moduli space of all disks with boundary on L. The picture is probably better than the picture, than the formula. You look at holomorphic disks with boundary on L in a given homology class beta, and mod reparametrization, but with one marked point on the boundary at which you have an evaluation map. So now you want to consider a suitably compactified and regularized version of this moduli space, and you want to push forward by evaluation at the boundary marked point. So basically you're asking which points of my Lagrangian L lie on the boundary of a holomorphic disk in the class beta. Okay, naively you might think that we'll trace a chain on L. I want to think of it as a cochain in some model for practical reasons. And then I will sum over all classes beta with weights, these coefficients z beta, weighted by basically the symplectic area and the boundary holonomy. And so this produces for me some cochain on the fiber with coefficients in K. Each term in here lives in a cohomological degree 2 minus the Maslov index. That follows from this dimension formula because, if I look at an n-3 plus Maslov dimensional family of disks, all the points on their boundaries, that's one dimension more, so the codimension of this is 2 minus Maslov. So, so anyway, I will not try to further justify too much what this achieves and why it's central in Floer theory. Well, maybe one thing I should say, sorry, is, formally, right, you can think of a baby version of Floer theory where there's essentially no holomorphic disks. That's a lie, but you can delete them temporarily and then add them back in. And what you would see is the Fukaya category as some kind of deformation of some kind of classical limit. And this deformation is governed by something in Hochschild cohomology, in which these kinds of coefficient would be actually the leading term. It's the part of Hochschild cohomology that has no inputs. Maybe this is not helpful. Okay, so now what we expect in life is that depending on the Maslov index, these disks will actually show up in certain codimensions as expected. And so in particular, we expect that the Maslov index 0 disks, the ones that don't meet the divisor D, occur along a union of codimension 1 walls in the base B. So we expect a generic fiber to not bound Maslov 0 disks, but when you move along a path in the base, you might pass through codimension 1 situations where you bound Maslov 0 disks. And then there will be some kind of wall crossing behavior, which I will tell you about on the next slide. So outside of these walls, the fibers are what's called weakly unobstructed in a tautological way. There's nothing below Maslov index 2. Maslov index 2 disks, this living degree 0 or dimension formula tells you they will want to pass through every point of every Lagrangian. They're a fact of life. And the count of the Maslov index 2 disks then gives you actually a function, because this is going to be a 0, degree 0 cochain, that just becomes a function which is a certain number, the degree basically of this evaluation map onto the Lagrangian L, sorry, FB in this case, times the weight. So this is a weighted count of the disks passing through a typical point of my typical Lagrangian. I build out of this a Laurent polynomial or series, and that becomes a function on the mirror space just because, well, it's like, sum of coefficients times monomials. And that's the superpotential. So back to Maslov 0 disks. So if I do have Maslov 2 disks and a superpotential, given by counting those disks, the expression that I get from this formula is going to be analytic just because these are integers and these are monomials in my coordinates. as long as the numbers don't jump. The problem is the counts of Maslov 2 disks will jump whenever you hit one of those walls where there are Maslov 0 disks. And so there's discontinuities due to bubbling of Maslov 0 disks. Pictorially, you might start from a Lagrangian which bounds a Maslov 2 disk in this class, and as you move to another fiber, that disk breaks into a union of two smaller disks, one of which still has Maslov index 2, the other has Maslov index 0. So this is additive under breaking because it's intersection number with D. And then, well, that disk has disappeared altogether, but the smaller one remains. So when you work out your superpotential, which enumerates disks, here actually you have, sorry, I didn't draw it to kind of not clutter, but the disk in the class beta also exists here. So here you had a z to the beta plus a z to the beta plus alpha. Here you lost the second term. And the solution to that is that there's actually wall crossing coordinate changes, in this case of a shape that will take z beta to the z beta times 1 plus z alpha plus maybe other things, which correct this discontinuity. So to those of you who are used to thinking of functions that are not continuous as in like basic analysis classes, you think of a discontinuity as the value of a function jumps. True. But here there's a more useful viewpoint, which is to think the domain of a function has jumped. And if you had corrected the way in which the domain was built, then the function would be continuous. And so the process of building the corrected mirror is to reglue the local pieces by these corrected coordinate changes that restore continuity. And so the art is to understand what is this wall crossing transformation. And so when you can do that, then you hope to build a mirror. And one of the key properties that was noticed early on in the early works of, I don't know if Maxim and Jan were first to observe this, and then Gross and Siebert used that. Is that correct? Yes, exactly. So so Kontsevich and Seubelman were first to observe that these wall crossing transformations, when you go around a codimension 2 locus where walls intersect, they want to be consistent. They should satisfy a co-cycle condition. And this, in fact, can be used to infer some unknown wall crossing transformations out of known ones. So the issue that I want to point out is if you have negative Maslov disks, then in fact consistency fails, or rather it needs to be amended by something that accounts for those disks. Okay, so I have an example which I don't want to tell you too much about because it's a bit boring and technical, but I just want to show that it exists and tell you what the outcome is. Because first thing when this happened is you're told like, oh, the sky might fall on your head. Like, well, can the sky actually fall on my head? You try to check. And so here's an example where it's very artificial and it's not compellingly a proof that this actually is something everybody should worry about. But it's a proof of concept that this can actually happen sometimes. So I take a toric fourfold, which is just c squared times the total space of O of minus 2 over P1. Okay? And so this is a toric Calabi-Yau fourfold. And then I will do some blow-ups of it in a way that I will on purpose make non-toric, even though that's obviously dumb because I could have made it toric. So I will blow up two codimension 2 loci. One of them lives over the fiber of O of minus 2 over a point I will call 0 in P1, times a complex line in C squared, which I will make parallel to the first factor, but I will place it at the second coordinate x2 equals 1. And the other one is similarly another fiber of O of minus 2, this time over infinity, times a line in C squared in the other direction. So blow up those two things. And we have technology for building an SYZ fibration on this space. On the complement of an anticanonical divisor, what's the anticanonical divisor? On a toric variety, you can just take the union of the toric strata. And when you take a blow-up, you can just take the proper transform of a toric strata. So just think of a toric strata of this thing. Outside of the exceptional divisors, what my tori look like is just the pre-images under the blow-up map of product tori in the space I started from. So we can calculate mirror things. For the toric case, this is just like routine by now with a known technology. You can check that a product torus in c squared times O of minus 2 bounds, in fact, 1, 2, 3, 4, 5, 6 families of Maslov index 2 disks, which basically look like disks that are parallel to coordinate axes. So Z1 is the weight I give, in terms of holonomy and symplectic area of a disk that's just a disk in the first factor of c squared, and everything else is constant. Same thing for Z2, and the other ones, they kind of run along, the axes, in quotes, of the toric variety, O of minus 2 over P1. There's an extra term here, which is a little bit funny, with Q squared times Z4, which warns us to looming danger. It's this disk which is inside a fiber of O of minus 2, union the zero section of O of minus 2. The zero section of O of minus 2 is a sphere with normal bundle degree minus 2. This is actually not regular. If you deform the complex structure a little bit, it will disappear. But the union of that sphere with that disk will deform to a smooth holomorphic disk, and that's why we have to count it. Okay, so that's what it is. And what's interesting here is we already see an occurrence of an interesting sphere. The zero section in O of minus 2 is a sphere with normal bundle O plus O, because it's trivial in the c squared factor, plus O of minus 2. The goal of these blow-ups was that if I do this construction not at a random point of c squared, but here at 1, 1, then this sphere is going to hit the two exceptional loci, and its normal bundle will become, after taking the proper transform, will become O of minus 1 plus O of minus 1 plus O of minus 2, which is kind of Chern number minus 2. This is something that has negative intersection number with the toric divisors. Okay, so there's a boring calculation that you can do to replicate this inside X, inside the blow-up. And now we have to watch out a bit that when you take a product torus, if your product torus is of small radius in c squared, then things are the same, because by maximum principle, holomorphic disks can't hit these lines at 1. But if the radius is more than 1, then there's something clever that your disk can do, or sneaky maybe, which is arrange that as it moves maybe in this factor in a certain way, it can also move in the c squared factor. And if it arranges to hit, when it crosses, say, for example, this blue line at 1, exactly when it hits this divisor at L0, then you get that intersection with the divisor to be discounted after you do the blow-up. After you pass to a blow-up, there's no more intersection. And so that opens a way for proper transforms of higher Maslov disks in the toric variety to become Maslov 2 disks. And that means we get extra terms in this count. So here's the formula in all of its splendor. There's 4 formulas depending on whether the radius of your torus in the c squared factor is less or more than 1, whether it encloses or not the blow-up locus. So in that corner, you get the same formula as for the toric case. And then here you get extra terms, which are disks. So these are disks that move in the first factor of c squared, and they also move inside the O of minus 2 in a way that they hit the exceptional divisor where otherwise they would have had an excess intersection with D. And you can do the calculation, and there's like 4 different answers. And then you know that you have wall crossing when one of your radii crosses 1. You can work out the wall crossing transformations coming from disk bubbling, and you get coordinate changes which are of a shape. Indeed, one of the coordinates get multiplied by some generating series for Maslov 0 disks that you hit along the wall, and the other coordinates are left alone. And now we have a problem, because if you look at these coordinate transformations, they actually do not satisfy the cocycle condition. There is a mismatch, that the composition of these two or the composition of those two are not the same. And that's basically because of the orange terms. All of the problems here are the orange terms. These orange terms come from exactly the contributions of things that manage to hit exactly the zero section of O of minus 2 at the point 1, 1, so that they incorporate this sphere with very negative normal bundle in them. And so somewhere in the middle of this diagram here, there is a Maslov index -2 disk that causes inconsistency in the wall crossings around it. Okay. So now the question you may ask is, what kind of space was this? Now the claim is, in some sense, the right mirror of this space is a space built by taking 4 coordinate charts, equipping them with these various functions, and you glue them along these coordinate transformations, and pairwise everything is fine. These are analytic spaces glued by an analytic coordinate change in a way that preserves the functions. Whoops. But there's an inconsistency. So sometimes I like to call this locally a space. And one way to think about this inconsistency you introduce, so if you linearize things with respect to this parameter that counts the weirdest disks in there, is to declare that this is a deformation of the algebraic geometry of the mirror where you ignore those orange terms by an element of, so if I want to be pedantic, the 4th Hochschild cohomology of matrix factorizations on this Landau-Ginzburg model, which means, so deformations of Landau-Ginzburg models are governed by the complex given by polyvector fields, but deformed by interior product with d of the superpotential. And so the leading term of this deformation is going to be a class which is a 2 cocycle in the Cech sense. So this is something on triple overlaps. This is like failure of compatibility of coordinate changes with coefficients in wedge 2 of a tangent by vector fields. Now this class, I take it to take values on the overlap of charts that goes around the center. I know I had 4 charts around. I need to kind of simplify and make it 3 so that it's a 2 cocycle, but so be it. And its value will be, well, this coefficient that's kind of in front of the bad terms times the bivector field dd log z1, dd log z2, which is kind of the basic vector field in the direction transverse to this kind of strange codimension 2 scenario. Now, technically, I need to complete this to a cocycle in this by adding other terms that are in the 1st degree Cech cohomology with coefficients in vector fields. And even in the functions, these are the orange terms. So all these terms on this slide are the orange terms in that picture. There's corrections to this term of the superpotential. There's corrections to these 2 gluing maps. And there's a correction to the Cech boundary of the gluing maps.
So, I'm confused by the slide. So the slide says there's something called x Cech comma w, which is an analytic space with a function that I can take matrix factorizations off. Mm-hmm. What is that mirror to?
So
if
I don't know exactly, but I think, in practice, so I don't have a theory of what this space is, and maybe that's a weak point. But in this case, it's the space if I work mod q prime, q double prime. Or if you want, if I ignore the orange terms. Okay. So that means if I set the limit where, in fact, the proper transform of that, that most strange sphere that shows up in the middle of my diagram has infinite area, but nonetheless, other spheres don't have infinite area yet.
So this is a situation where the negative Maslov index disk has
weight 0. Yes, so its weight becomes 0, but the others have not been messed up. And I don't think this is always realistic or possible to do, but you could try to isolate basically the negative Maslov disks from the rest of the story, and that's what I'm doing here temporarily. I don't think this is a wise thing to do in general, but in this example, it kind of helps get into the picture. And then, yes, so basically, in this case, we can treat this mirror as an actual deformation, not just a first-order deformation, an actual deformation of an honest Landau-Ginzburg model, which was what you got if you kind of fudged things about this negative disk. And so the outcome is you have a space with a locally analytic function, but the coordinate charts don't satisfy the cocycle condition by an amount which is, in fact, the interior product of dw into this class.
So is it some sort of gerb?
So people keep asking me that, and I don't think it quite is, because a gerb is a way of deforming the notion of functions on a space that's well defined.
Functions like two forms his bivector field.
Yeah, it's not in O. It's a two-form in bivector fields, not in O. It's a way of modifying the gluing. I mean, maybe it's a gerby structure on the tangent in some way. I don't know, on the tangent complex or something, but it's not what's usually meant by gerbs. Okay.
It's Poisson structure.
Yes, probably. It's probably something like quantization, Poisson structure, something like that. It's not really a gerb in the usual way. Okay. All right. So yeah. So this was meant to just tell you that these things can happen. So I want to quickly tell you a little bit about how we can hope to kind of understand these deformed geometries in general, what they should look like, and how we might kind of restore some sanity into things, maybe or maybe not. So first thing I want to do is start again from a Lagrangian torus fibration, take the uncorrected mirror of a smooth part, and I will consider coefficients for Floer theoretic calculations for holomorphic disks, not just with boundary on a fixed Lagrangian fiber, where I would use Novikov coefficients, K, but actually on possibly moving families of fibers, which means these weights Z beta, or if you want these monomules in Z1 Zn, become first-class citizens. So in fact, I can define a sheaf on B whose values on given, maybe let's say polyhedral opens, maybe something like that, are going to be, in fact, the regular functions on this mirror on the set of things whose valuation image is that given set in B. So concretely, this is a completion of Laurent polynomials in Z1 to allow infinite sums as long as they are guaranteed to Novikov converge everywhere in the open I'm considering. This is exactly the kind of sums I will get out of Floer theory for the fibers inside that region of B. And so now I can do Lagrangian Floer theory, not just for disks with boundary in a single fiber, but letting the fiber move simultaneously, and using what I will call universal weights in this, coefficients in this ON. So I will just count again disks, but now letting which fiber they have boundary on very freely. And I will count them with a weight, which is again this Z beta, but Z beta now becomes a local analytic function on the mirror with positive valuation where any given disk can occur. So if the valuation of Z beta becomes negative, if this variable becomes too large, that means the area of that disk would become negative. I know it cannot be a holomorphic disk anymore. Okay, so terms that exist somewhere always have positive valuation. So this produces, in principle, a cochain on B0 with coefficients in cochains of the fiber with coefficients in this ON sheaf. Okay, this is just a way of saying I look simultaneously at all the boundaries of all the holomorphic disks bounded by all the fibers, well, the smooth fibers, and with weights corresponding to their areas and holonomies, and I make that into something that's basically a cochain on the uncorrected mirror with coefficients in analytic functions. So what do we expect? First, the expectation, one first expectation, is that Maslov 2 minus 2i disks show up along codimension I walls in the base. The heuristic argument for this is they should occur roughly along complex or analytic or something loci, at least in the tropical limit of codimension I, complex codimension I. And in the tropical limit, complex codimension I loci should have codimension I in the base and codimension I in the fiber, which is why I expect things to localize in equal degrees in base and fiber. The second hope is that this M0 thing satisfies something called the master equation, which looks like basically the classical boundary of this cochain, plus something which is like some kind of degree -1 bracket applied to this, and itself cancels out. So what this expression is supposed to express is the fact that the boundary of a moduli space of holomorphic disks is situations where your disks have broken into a pair, a union of two holomorphic disks attached together at a boundary point. In practice, well, so there's wonderful work of Kenji Fukaya and Kei Irie to prove this with loop space coefficients. If you don't introduce further loop space coefficients, it's dubious whether this holds at chain level, whether you need an L infinity deformation. This is kind of maybe a slightly optimistic expectation. But let's assume we have that. So first, what is this bracket? So there is a bracket on Laurent polynomials with coefficients in the first homology of a fiber, with values in cohomology of a fiber, using the fact that this is in fact a polynomial algebra and an exterior algebra on the same thing. And so what I can do is I can use the exponent gamma, basically the loop, which is the boundary of a disk, to insert it into the cohomology classes by interior product and decrease by 1 the cohomological degree. And so I can combine that with the exterior product and skew symmetrize to produce a degree -1 bracket on this cohomology with coefficients in the loop, in the group ring of the first homology. What this is in more grown-up language is this is the so-called Chess-Sullivan string bracket on the homology of a free loop space of a torus.
So this is a Gersten-Haber algebra, yeah?
I believe so, yes.
A bracket of polyvector fields.
Yes, yes, exactly, yes, it's going to come. So extend with the cup product and so on. And now you can pass it through mirror symmetry, because basically the cohomology of a fiber turns into exactly polyvector fields on the uncorrected mirror space. And the nice thing that happens is that this Chess-Sullivan string bracket up there turns into the Schouten-Neon-Haus bracket on polyvector fields. And the master equation that you hope M0 satisfies becomes a similar equation on something I called bold W, which is kind of a generalization of the superpotential that includes all Maslov index disks. So the outcome of this is you have, this thing which is the transcription on the mirror of M0, which lives in, so there's basically functions on the uncorrected mirror, and there's vector fields on the overlaps, and there's bivector fields on the triple overlaps, and so on. And this master equation basically says that, classical differential plus Schouten bracket with W forms a differential on this complex. And if you unpack it term by term, it says the part that's of degree 1 that corresponds to Maslov 0 disks, you can think of as a deformation of analytic structure. So in the Cech model, this would be deforming the gluing of charts Ui and Uj by a vector field on the overlap. In the Dolbeault model, you would deform the del bar operator by changing the complex structure. And then the first equation here says that the leading term, the classical superpotential, is analytic with respect to this deformed structure. That one says that this deformed analytic structure is actually not quite an analytic space because of this error term. And this is, in the Cech world, this is the failure of the coordinate changes to form a cocycle condition. In the Dolbeault world, you could try to think of it as a deformation to a non-integrable, almost complex structure. Regardless, because this failure involves interior product with dW, the critical locus of the leading thing is still an honest analytic space with consistent gluings around it. So these deformed Landau-Ginzburg models still have a classical well-defined critical locus, including probably the derived critical locus and so on. So the hope is you can still do geometry on these spaces.
So loop space of the torus, but all components of this are contractible. So you
No, free loop space. So each component looks like a copy of the torus. Right? Oops, wrong way. Free loop space. So that's why, this term here is the components, right, homology classes, and this term here is the torus itself, position of a base point. Yes?
You get polyvector fields, but then we should have a quotient complex which is a difference, and then different formality morphism should also enter the game in some way. Yeah.
Yeah. So something is fishy in the details here. Yeah. Okay. Yes, I agree. This is only like a linear approximation to what should be true. Something like that. Yeah. So let's not. Okay. So instead, I wanted to end with something slightly newer, maybe, which is how can we make this concrete in practice to define this algebra structure, and how can we go back from there to Fukaya-Floer theory? How do you build a functor from the Fukaya category to these new geometries? So fix a Morse function on your space, and to be more concrete, start by fixing a triangulation. I'm going to go to the next slide where this is spelled out. So I pick a triangulation of the base somehow, and I pick a Morse function on the base by putting a minimum at each vertex. Then on each edge I will put a saddle point, and so on and so on. So I can build a Morse function who's basically with one critical point in each cell of index equal to the dimension of the cell, and whose ascending manifold, whose descending manifold is exactly that cell. The ascending manifold is instead the star of that cell. And then I can add a perfect Morse function on the fibers to produce a Morse function on the total space. The Morse complex of that function is a version of the Cech complex of the base with coefficients in the cohomology of the fiber. Basically because Morse trajectories look like Morse trajectories in the base, which kind of look like Cech stuff, plus nothing happens in the fiber. So, whoops. Okay. So do this in this way, and now the Morse complex, I said, looks like Cech complex of the base with coefficients in the cohomology of the fiber for the open cover of the base by stars of the vertices. Now let's try to define Floer operations on this Morse complex. There's a classical idea for Floer cohomology for a single Lagrangian. I didn't even put their names here, this is terrible. Charest and Woodward, following earlier ideas of various people through Biran and Cornea and Lalonde, defined a model for basically Fukaya-Floer theory, where you look at the critical points, the Morse complex of a given Morse function, and besides just Morse flow lines and flow trees, you add in holomorphic disks with boundaries on your Lagrangian. So here now do the same, but for flow lines of a Morse function on the total space. So the flow lines move from fiber to fiber, and then they're allowed to break through holomorphic disks with boundary on that fiber that you are at that moment. So the claim is, okay, you can count such gradient flow trees, suitably regularized, with weights corresponding to all of the disk content. There are ways to achieve transversality by elementary methods, and there is a convergence with Novikov coefficients as long as this subdivision P is fine enough that I started with. I want to kind of cut finely enough. That's for the experts. So the coefficients I will take for this Morse complex, I said coefficients in ON. Concretely, I mean quantities which Novikov converge over the whole open star of a given cell. Why? Because that's exactly where all the Morse flow trees from my given critical points can go, possibly. And so I need to know that when I evaluate at those points, the symplectic areas of trees of holomorphic disks will still be positive. So that's the natural convergence condition. And so if I do that, so my Morse complex, before I start putting more stuff on, is exactly the Cech complex of the uncorrected mirror with coefficients in polyvector fields, using the cover of the naive mirror by aphenoid domains that are exactly the things that map to the stars of the given cells, of the vertices. And then Floer operations that include holomorphic disks on top of those trees will deform the Morse complex by counting tree disks, and that will incorporate all of the deformations needed. So the claim, just conjecturally, is this produces a curved A-infinity algebra, which is a suitable version of the Cech complex of a corrected mirror now, including the bracket with this full superpotential, or something like that. sorry, so maybe same comment as what Maxime said about the previous slide. Maybe this is a little bit of a, aspirational statement, but somehow I think this algebra A that comes out of this construction should be the corrected mirror in this kind of incarnation, roughly.
No, I think it was culprit. It's you consider just cohomology of fiber.
Yes.
It's actually some chains in fiber, and then if you consider actual disks, you get
possibly. I mean,
more complicated things. Just
I don't know. I mean, eventually the cohomology of a fiber becomes just like a Morse complex. I'm actually doing a Morse complex anyway. But maybe what you're saying is my Morse complex might not be fine enough to capture all the. I don't know. I mean, I'm kind of, for now at least, attached to the idea of having a Morse model that comes from a Morse function of the total space and just trying to interpret it in terms of geometry of a mirror.
Polyvector fields, it's just an approximation to polydifferential operators here. Okay. I'm not sure if I want to go all the way to polydifferential operators, but but then I cannot deform infinity algebra just with polyvector fields.
okay.
You cannot do it. Yeah. That's
Okay, I think we need to talk. Okay. All right. So I just wanted to say, okay, so the next, the last thing I wanted to say, oh, sorry, I'm over time. Okay, so basically, advertisement, there's a Fukaya-Floer functor that should work for Lagrangian sections, but so two things that were previously solved that this does not solve are how to deal with the singular fibers and also how to deal with Lagrangians that are not sections. But the plan is there's a Fukaya-Floer functor. This will be the thesis, hopefully, of my student Keely Hook to flesh out this. For given a Lagrangian section, you produce something that will be a module over this algebra, basically out of Morse theory of the restriction of a function to the Lagrangian, and the structure maps come from configurations that involve holomorphic disks with boundaries on that Lagrangian and tree disks with boundaries on the fibers. And then there's actually a bimodule basically over sections and the algebra of the previous slide, which gives you a functor from Lagrangian sections to modules over the algebra. This is as in Kenji's talk, but different setting. By counting these mixed pictures where on one side you have Lagrangian sections and their intersections, and on the other side you have Lagrangian fibers of the SYZ fibrations and trees and Morse flow lines. Okay, I think this is, sorry, I'm over time, but thank you.
Thank Denis for the wonderful talk. Now you can understand why I learned to teach multivariable calculus by watching videos of his lectures at MIT. Now, are there any questions?
So I'm not sure I got the point. You have a way to associate from one workout element another one. Does this come from an A infinity or L infinity or G infinity morphism at the chain level?
I think, at the classical level, yes, but ultimately I'm not really interested necessarily in the Maror-Cartan element itself, but rather in the finished product. I was just, trying to explain, the problem was when you introduce a new algebra that you say, oh, this algebra is the mirror. I mean, I hate kind of non-commutative geometry in that, like, it gives you an algebra and it claims this is a space. So my brain wants to say, yes, this is a space in the sense that naively, if I forget the terms that are kind of too painful to contemplate, this starts like a Landau-Ginzburg model, but then I've modified it in these various ways by these cocycles. And so indeed, at the level of the uncorrected mirror, you can just transcribe because basically, cochains with coefficients in cohomology of a fiber become cohomology of polyvector fields on the uncorrected mirror. To actually understand the geometry of a deformed thing, you probably just have to follow the recipe, produce your curved infinity algebra, and then stare at it to try to understand what is this thing trying to tell me that is a space-ish in some way. And so Maxime is telling me it's actually not really polyvector fields.
Yes.
Yeah. Okay. But can it be something of a similar dimension in terms of the size? Oh, okay. Then I'm happy.
The same, but the brackets are different.
Okay. Yeah. So the bracket is different, and it's not polyvector. It's something that looks the same size as polyvector fields, but is no longer polyvector fields. Okay. I can live with that. Thank you. Yes.
So this curved infinity algebra you mentioned, Good chains on C on X dual.
Yeah.
Do you expect it to correspond to something known, just in terms of X on the other side, or?
So this algebra is constructed from X, right? Because it's built from Floer theory, Morse theory deformed by holomorphic disks in X. And again, so in the case where the mirror is an honest Landau-Ginzburg model, well, okay, if it's, in the Calabi-Yau case, it should just be polyvector fields on the actual mirror Calabi-Yau rather than on the uncorrected mirror. In the case for Landau-Ginzburg model, I think it's this thing with like polyvector fields deformed by the superpotential. In the more exotic things, it's probably something weirder that I didn't capture properly.
I'm not sorry, I want to correct myself. Polyvector fields are quasi-isomorphic to coefficient complex, but this quasi-isomorphism is high non-trivial. It should be built in this.
It requires drink field associated.
Yes, exactly. Yeah.
Yes. Yeah, but my guess is also on the symplectic side. By the time that this thing has had all of its deformations, the way in which A matches with the Hochschild cohomology of the Fukaya category has also been messed up, probably.
Okay, other questions?
Yes.
For the blow-up example on page 7, is it clear how the associated Gauss-Manning connections for this potential decomposes according to the A model?
This thing might not even have critical points yet because this is an open manifold. At least the Fukaya category of this thing is trivial. So if you want a more interesting example, you can just compactify by, closing up to P1 times P1 times here's the Bohr surface. And you can find formulas in my paper if you really want. I haven't computed anything about what actually happens. I expect this will still have isolated critical points where you will not see anything strange happening. This is probably semi-simple.
Any other questions?
So you constructed a mirror at Cech from this counting of X, and which categorical statement can be made from this mirror pair?
I think basically what this is converging to is that you can embed the Fukaya category of X into modules over this algebra A. And I'm not fond of things that say the end thing is algebraic, but so what I'm trying to say is you should think of the algebra A as some kind of suitably modified version of polyvector fields on a mirror space.
Regarding this Landau-Ginzburg model of X-Cech, can the Fukaya category of X related to the metric factorizations or category of singularities of the LG model?
Yes, so well, matrix factorizations of the LG model, but that's already probably in Hang Yuan, I believe, with more powerful, more robust methods than this, because it also handles things that are not sections and singular fibers are.
But assuming that there's no negative.
Assuming no negative Maslov disks. When there are negative Maslov disks, then bets are off about whether the mirror is actually a Landau-Ginzburg model.
Thank you.
Okay.
Okay. Other questions? Okay, let's think.